Before the oceans of today had their familiar names, before the Pacific stretched across the map in its present form, before the Atlantic opened between the continents, Earth carried other seas. They were older, stranger, and almost entirely gone. Their waves no longer move under any sky. Their coastlines have been folded into mountains, buried beneath continents, or swallowed into the mantle. Their floors have vanished through the slow recycling of plate tectonics. Yet their traces remain, faint and patient, written in stone, minerals, fossils, and the chemistry of the air. The modern ocean feels permanent because human time is brief. The Pacific seems endless. The Atlantic seems ancient. The Indian Ocean seems fixed between continents. From a shoreline, the sea appears to be one of the great constants of the world, rising and falling with tides, darkening under clouds, brightening under the sunday. But in geological time, oceans are temporary. They are born, they widen, they age, they shrink, and eventually many of them disappear. A sea that once divided continents may close so completely that its only memory becomes a mountain belt. A basin that once held warm, shallow water may become dry land. A vanished ocean may leave behind nothing that looks like water, only rock. This is the quiet mystery of prehistoric Earth. The planet has not always worn the same face. Its continents have drifted, collided, broken apart, and gathered again. Its oceans have opened like dark blue wounds between separating lands, then closed as plates move toward one another. Each lost ocean has carried its own climate, chemistry, currents, and living worlds. Some are so ancient that their names are known only through reconstruction. Some existed before animals. Some witnessed the first oxygen entering the seas. Some lay beneath ice when Earth nearly froze from pole to equator. Some became highways for evolution. Others became graves for entire ecosystems. To follow these forgotten oceans is to follow the deeper memory of the planet. It is not a journey across a single map, but through many maps layered over one another. In one age, Earth is a young world of steam, volcanic gas, and heavy rain, where the first basins begin to fill with hot mineral water. In another, microbial mats spread across shallow seas, building stone structures grain by grain beneath a quieter Sunday. Later, a vast superocean surrounds a supercontinent, holding the planet in a long age of oxygen-poor depths and hidden biological preparation. Then ice spreads across the globe, sealing the seas beneath a frozen lid, while life survives in small pockets of warmth and brine. After the thaw, oceans return as engines of renewal, carrying nutrients, oxygen, and the conditions for more complex life. The first important truth is that oceans are not merely empty spaces filled with water. They are active planetary systems. They store heat, they dissolve gases, they move nutrients, they shape climate, they erode continents and build sediments. They create habitats where life can begin, persist, and transform. When an ocean disappears, its influence does not disappear with it. The water may move elsewhere, but the sediments remain. The chemistry remains. The fossils remain. The mountains raised from its closing remain. Even the atmosphere can carry the legacy of an ancient sea, because oxygen itself rises through the work of organisms that once lived in prehistoric waters. This gives the lost oceans a strange afterlife. They are gone as places, but not as forces. A band of iron ore may once have been dissolved metal in an oxygen-starved sea. A limestone cliff may once have been the floor of a warm, shallow ocean. A mountain range may mark the place where two continents closed an ancient basin between them. A fossil shell in a desert may show that the desert was once beneath water. The present landscape is full of these quiet reversals. Dry land remembers seas. Stone remembers currents. Air remembers microbes. The earliest oceans are especially difficult to imagine because they belong to a world without familiar life. There are no fish, no corals, no whales, no forests along the shore. The land is mostly bare rock. The sky is thick with gases that would not support animals. The ocean itself may be warm, acidic, metal-rich, and dark with dissolved minerals, yet within such hostile water, the first steps toward life may have taken place. A world that seems severe from the perspective of modern organisms may still be rich in chemical possibility. The beginning of life does not require comfort. It requires water, energy, molecules, surfaces, and time. The forgotten oceans also reveal that life and geology cannot be separated. Microbes change the ocean, and the ocean changes microbes. Cyanobacteria release oxygen, and the ocean first consumes that oxygen by rusting dissolved iron. Over millions of years, this process helps reshape the atmosphere. Later, oxygen becomes more available, allowing new forms of metabolism and eventually more complex organisms. What begins as microbial chemistry in ancient water becomes one of the foundations of animal life. The breath of later creatures depends on seas that existed long before animals had lungs, gills, or bodies large enough to see. There is a gentle scale to this story. Even when the events are immense, the lost oceans do not vanish in sudden dramatic moments. They change slowly, through plate movement, cooling climate, chemical reactions, and biological persistence. Their histories unfold in layers. Sediment settles grain by grain. Microbial mats rise layer by layer. Continents drift by distances too small to notice in a lifetime, yet enough to close an ocean across deep time. The pace is slow, but the consequences are vast. The journey through these prehistoric oceans is therefore a descent into Earth's older rhythms. It moves away from the noise of the present and into a world where time is measured by the shifting of continents, the building of rocks, the breathing of microbes, and the rise and fall of entire seas. The surface of the modern ocean may still move with waves, wind, and light, but beneath that familiar surface lies a much older story. Every sea today is part of a lineage of vanished waters. Every coastline is temporary. Every ocean basin is a chapter, not the whole book. In the beginning of this journey, the planet appears not as a finished world, but as a changing one. Its waters are restless. Its crust is mobile. Its atmosphere is unfinished. Its life is small, patient, and powerful in ways not yet visible. The forgotten oceans of prehistoric Earth are not distant fantasies. They are the hidden foundations of the world that exists now. They shaped the climate, fed the first ecosystems, carried the chemistry of life, and left behind clues that still wait inside rock. Their waves are gone, but their story continues, quietly, beneath the present Earth. An ocean begins when the solid skin of Earth pulls apart. It may start as a long crack across a continent, a valley slowly widening under the pressure of deep forces below. The land thins, faults open, volcanoes rise along lines of weakness. Lakes gather in the low places, rivers deliver sediment, magma pushes upward through fractures. Over millions of years, the rift deepens and lengthens until the continent is no longer one continuous body. Seawater enters. A narrow sea is born. This is the first stage in the life of many oceans. They do not appear as finished blue expanses. They begin as wounds in the crust, as rift valleys, inland basins, and young seaways. The Red Sea offers a modern glimpse of this process. It is not yet an ocean as wide as the Atlantic, but it shows how continents can separate and how new oceanic crust can begin to form between them. In deep time, a similar process opens the Atlantic itself as Pangaea breaks apart. Long before that, other oceans open between older continents, now rearranged beyond easy recognition. Once an ocean opens, it grows through seafloor spreading. At mid-ocean ridges, molten rock rises from the mantle, cools, and becomes new oceanic crust. The new crust pushes older crust outward on both sides. This process is slow, often only a few centimeters each year, but across millions of years it becomes enormous. A narrow sea becomes a wide ocean. Coastlines drift apart. Marine habitats expand. Currents reorganize. Climate changes because water can now move through new gateways between continents. The birth of an ocean is never only a geological event. It changes the circulation of heat, salt, nutrients, and life. The young ocean is warm near its spreading ridges. Hydrothermal vents release mineral-rich fluids into deep water. Basaltic crust reacts with seawater, altering the chemistry of both rock and ocean. Sediments begin to accumulate on the new floor. At first, the crust is high and hot. Later it cools, grows denser, and sinks lower. The basin deepens. More sediment gathers above it. Over time, the ocean matures into a vast system of ridges, plains, margins, currents, and ecosystems. The life of an ocean is connected to the movement of plates around it. If the surrounding plates continue to pull apart, the ocean grows. If the motion changes and subduction begins along its margins, the ocean may start to shrink. Subduction is the process by which dense oceanic crust bends downward beneath another plate and returns into the mantle. It is a quiet but powerful act of recycling. The seafloor that once formed fresh and hot at a ridge eventually cools, ages, and descends. In this way, the same planet that creates oceans also consumes them. This cycle is sometimes called the Wilson cycle, named for the idea that oceans open and close through repeated tectonic stages. A continent breaks apart. A new ocean forms. The ocean widens. Subduction begins. The ocean narrows. Continents collide. A mountain belt rises where water once lay. Then, after long spans of time, the process may begin again in a different place. Oceans, therefore, have biographies. They have childhoods, maturity, decline, and disappearance. The Iapetus Ocean is one example of a vanished sea. It once separated ancient landmasses that later become parts of North America, Greenland, Scandinavia, and the British Isles. During the early Paleozoic era, it holds marine life in its waters, while continents slowly approach one another. As the ocean closes, sediments, volcanic arcs, and seafloor fragments become compressed. Mountain-building events help assemble new continental connections. Today, traces of the Iapetus Ocean survive in rocks across both sides of the North Atlantic region. The water is gone, but its closure helps shape later landscapes. The Rake Ocean follows another chapter of Paleozoic geography. It opens as landmasses separate and later closes during the assembly of Pangaea. Its disappearance contributes to mountain belts and the union of continents into a supercontinent. These names may sound distant, but the pattern is familiar across Earth history. Oceans are born from separation and die in collision. Their deaths create mountains, sutures, mineral belts, and records of lost worlds. A powerful insight comes from recognizing that mountain ranges can be ocean graves. When two continents collide, the ocean between them is usually destroyed first. Its crust subducts. Its sediments are squeezed. Fragments of seafloor may be pushed upward onto land as ophiolites, rare slices of oceanic crust preserved on continents. Rocks that once formed under deep water can end up high in rugged terrain. The Himalayas, formed by the collision of India and Eurasia after the closure of the Tethys Ocean, show this principle in a later and dramatic form. Marine fossils found high in such mountains reveal that the summit world once belonged to the sea. The ocean's life cycle also affects climate. When continents are arranged in one way, ocean currents carry heat along certain paths. When an ocean opens, currents may reach new regions. When an ocean closes, circulation can be restricted. The opening of gateways can cool or warm climates, influence ice formation, and change rainfall patterns. Modern climate depends deeply on ocean circulation. Ancient climates did as well. A vanished seaway may have altered the movement of heat across the globe, influencing ecosystems far beyond its shores. Nutrients follow geography too. Continental shelves are often rich biological zones because rivers deliver phosphorus, iron, and other materials from land. If a new ocean creates long, shallow margins, life may find expanded habitat. If a supercontinent reduces shallow marine area or alters runoff, productivity may change. Ocean basins are therefore not only containers, their shapes help decide where life flourishes and where it remains sparse. Even the deep ocean floor is part of this cycle. Oceanic crust is mostly basalt, denser and thinner than continental crust. Because it is continually created and destroyed, it is much younger on average than continents. This is why the present seafloor preserves only a small, recent portion of ocean history. Most ancient ocean floors are gone. The oldest oceans must be reconstructed from fragments caught in continents, from sediments, from isotopes, and from the scars of ancient collisions. Earth erases its ocean floors as part of keeping the system alive. This erasure is not a failure of memory, but the method of the planet. By recycling oceanic crust, Earth moves water, carbon, sulfur, and other elements into and out of the mantle. Subduction feeds volcanism. Volcanism returns gases to the atmosphere. Weathering draws gases down again. The life cycle of oceans is connected to the long-term habitability of Earth. A world without such recycling would preserve more of its surface, but might lose the dynamic balance that makes climates and oceans endure. In this way, the forgotten oceans are not separate episodes scattered through prehistory. They are expressions of a repeating planetary rhythm. Water fills the basins that tectonics opens. Life adapts to the currents and chemistry those basins create. Sediment records the passing conditions. Then plates move on. The ocean narrows, closes, and leaves its remains inside mountains or beneath younger rocks. Another ocean opens elsewhere, carrying forward water, chemistry, and life into a new arrangement. The modern map is only the latest pause in this cycle. The Atlantic continues to widen in some regions. The Pacific is ringed by subduction zones and is gradually being consumed along many edges. The Mediterranean is a remnant of larger ancient seas linked to the Tethys realm. The Red Sea is a young opening basin. Around the planet, oceans are not fixed features, but moving chapters at different stages of their lives. The prehistoric oceans of Earth are forgotten because they no longer appear as water. Yet their stories remain in the architecture of the planet. They are found in folded rocks, volcanic arcs, continental shelves, ancient sediments, and the paths of mountain chains. They remind the present world that the sea is not only a surface of waves, it is a temporary expression of deep motion. Every ocean has a beginning, a long middle, and an eventual transformation. In the slow breathing of plate tectonics, water follows the changing shape of stone, and the face of Earth is rewritten again and again. More than 4 billion years before any modern ocean takes its familiar shape, Earth is not yet the calm blue world known today. It is young, restless, and still carrying the heat of its birth. The planet turns beneath a dimmer young sun, wrapped in a sky that would seem heavy and unfamiliar. There are no forests, no reefs, no birds crossing the air, no continents shaped into recognizable outlines. There is only a raw planetary surface, changing under fire, impact, vapor, and stone. The early Earth forms from collisions. Dust and rock gather in the young solar system, striking, merging, heating, and growing into a world large enough to hold itself together by gravity. Each impact adds more material and more heat. Radioactive elements inside the planet release energy. Dense metals sink toward the center, helping form the core, while lighter silicate rocks rise above. This separation is not gentle. It is a deep internal sorting, a vast transformation of molten matter into layers. The Earth begins to organize itself, but it does so through heat. During the Hadean Eon, the surface is often imagined as a world of glowing rock and unstable crust. In its earliest stages, much of the outer planet may have been molten, forming a magma ocean. The term does not describe water, but liquid rock, a searing sea of silicate melt spread across wide regions of the young surface. As heat escapes into space, this molten exterior begins to cool. Thin crust forms in places, breaks, sinks, remelts, and forms again. Nothing remains steady for long. The ground itself is temporary. Above this surface, the atmosphere is not breathable. Oxygen is almost absent. The sky is shaped by gases released from the interior through volcanic outgassing, and by materials delivered through impacts. Water vapor, carbon dioxide, nitrogen, sulfur compounds, methane, and other gases gather around the planet. The air is thick with chemical possibility, but it offers no comfort to later forms of life. There is no ozone layer to filter ultraviolet radiation. The upper atmosphere receives harsh sunlight, while below, volcanic gases and heat create a dense, unstable envelope. The Moon is already present, formed after a giant impact between the young Earth and a Mars-sized body early in planetary history. That collision changes the planet forever. It strips, melts, and reshapes large portions of Earth, while debris orbiting the planet gathers into the Moon. In the ages that follow, the Moon is much closer than it is today. Its pull on Earth is stronger. Tides, once oceans exist, may be immense compared with modern tides. Even before stable seas spread across the planet, the Earth-Moon system is setting rhythms that will later influence coastlines, shallow waters, and perhaps the environments where early chemistry becomes more organized. For a long time, surface water struggles to remain. The young planet is hot, and impacts are frequent. Asteroids and comets continue to strike, releasing energy powerful enough to melt rock and vaporize water locally or even globally during the most severe events. The early solar system is still crowded with debris. The Earth is not floating peacefully through empty space, but moving through a region where leftover bodies from planet formation still cross its path. Each large impact becomes a temporary return to fire, yet water is already part of the planet's story. Some of it may be trapped within the minerals and material that built Earth from the beginning. Some may be added later by water-rich asteroids and possibly comets, though modern evidence tends to favor asteroidal sources as a major contributor. Volcanic outgassing releases water vapor from the interior. In the earliest atmosphere, much of this water remains suspended as steam, forming part of an intense greenhouse blanket. The young Earth is therefore not dry in a simple sense. It is wet, but much of its water is held in the sky as vapor, waiting for the planet to cool enough for rain. Cooling is one of the great quiet forces of early Earth history. Space receives the planet's heat slowly. The surface hardens more often. Bombardment lessens over time. The crust becomes more persistent. Eventually, temperatures fall low enough for water vapor to condense. The first rains begin. These rains are not brief showers moving over soil and grass. There is no soil in the modern sense. No rooted plants to hold land together. No rivers shaded by trees. Rain falls onto black volcanic rock, fresh basalt, ash fields, impact basins, and fractured crust. The rainfall may continue for immense spans of time, perhaps in repeated storms across thousands or even millions of years, as the atmosphere and surface move toward a new balance. Drops strike hot rock and hiss back into steam. Steam rises, cools, condenses, and falls again. The cycle repeats across a barren world. Water gathers in low places. It runs through cracks. It fills basins created by impacts and by the uneven cooling of the crust. Slowly, the first long-lived oceans begin to appear. These early oceans are not the clear blue seas familiar from the modern planet. Their chemistry reflects the world that gives birth to them. Carbon dioxide dissolves into the water, making it more acidic than modern seawater. Sulfur gases from volcanoes add further chemical intensity. Hot basalt reacts with the young ocean, releasing elements into the water. Iron, abundant in reduced form because oxygen is scarce, dissolves easily and remains in solution. Without oxygen to rust it out, this iron can accumulate. The sea may carry a greenish or dark mineral tint, a metal-rich water under a hazy sky. This is a crucial insight into early Earth. The first oceans are not merely containers for life. They are chemical reactors. They receive gases from the atmosphere, minerals from the crust, heat from below, and energy from sunlight and impacts. Every shoreline, every crack in the seabed, every volcanic island becomes a place where water and rock exchange atoms. The ocean begins to alter the crust, and the crust alters the ocean. Even before biology becomes important, Earth is already a planet of cycles. The surface remains dangerous. Ultraviolet radiation reaches down through the atmosphere. Large impacts still occur, though less often than before. Volcanoes release gases and lava. The crust is thinner and hotter than modern crust. The ocean itself may be warm, perhaps even hot in many regions, especially where geothermal heat is strong. But danger and possibility exist together. Heat drives reactions. Minerals provide surfaces. Water allows molecules to move, dissolve, concentrate, and recombine. The harshness of early Earth does not prevent complexity. It helps create the conditions in which complexity may begin. The young ocean floor is especially important. As the planet cools, volcanic crust forms beneath the water. Cracks open. Seawater seeps downward into hot rock, reacts with minerals, becomes enriched with dissolved chemicals, and rises again. This process creates hydrothermal systems, places where geology and water meet in concentrated form. In the modern ocean, such systems support life without sunlight. On the early Earth, similar environments may have offered stable chemical gradients, mineral surfaces, and protection from surface radiation. They are not yet proof of life's origin, but they represent one of the strongest settings in which early prebiotic chemistry could have advanced toward biology. Above these young seas, the atmosphere slowly changes through interaction with the surface. Carbon dioxide dissolves in rainwater and ocean water. Chemical weathering begins to remove some carbon dioxide from the air and lock it into minerals. Volcanism returns gases to the atmosphere. This balance is primitive compared with the later carbon cycle, but the outlines of planetary regulation are already forming. Earth is not static. It responds. Its air, water, rocks, and interior are linked from the beginning. There are still no animals, no plants, and no complex ecosystems. The land is bare rock under a strange sky. The ocean is dark, warm, mineral-rich, and restless. Yet in this world, the foundations of everything later are quietly being laid. The presence of liquid water allows the planet to become chemically active in a special way. The early atmosphere supplies carbon and nitrogen. The crust supplies metals and mineral surfaces. The moon helps shape tides. The cooling interior creates gradients of heat. Each element of the young planet contributes to a slowly forming stage. The connection to the modern world is hidden but profound. The oceans that now soften climate, feed clouds, store carbon, and cradle marine life trace their ancestry to these first rains. The oxygen now breathed by animals depends on later life that begins in a world without oxygen. The rocks beneath modern continents carry fragments of ancient crust that survived from these early chapters. Even the deep ocean trenches of the present belong to a planet whose surface has been recycling itself since youth, swallowing old crust and making room for new. In the Hadean and early Archean, Earth is not yet welcoming, but it is becoming habitable. Its fire is cooling into stone. Its vapor is falling into water. Its poisoned sky is beginning a long transformation. Its oceans are gathering in basins beneath clouds of steam and volcanic haze. The planet does not yet look alive, but the conditions that make life possible are assembling in silence. One storm, one mineral reaction, one cooling surface at a time. The first oceans gather beneath a sky without blue clarity. They do not resemble the wide, calm seas of the present world, with sunlight scattering through clear water and white clouds drifting above. They are younger, darker, heavier with dissolved chemistry. Their shores are not lined with sand, mangroves, shells, or reefs. They meet black volcanic rock, fresh lava fields, unstable crust, and steaming slopes. The land around them is bare and newly hardened, with no roots to hold it, no soil to soften it, and no living green to interrupt the mineral silence. These waters form from a planet still warm inside and restless outside. Rain falls from an atmosphere rich in water vapor and carbon dioxide, then strikes rock that has only recently cooled from molten heat. The water gathers in basins and lowlands, but it does not stay chemically pure for long. It begins to react. It seeps into cracks, washes over basalt, dissolves gases, pulls ions from stone, and returns again to the growing ocean changed by every contact. The first seas are not passive pools. They are immense, warm laboratories spread across the young surface of Earth. Their color may be one of the first surprises. The modern ocean often looks blue because water absorbs longer wavelengths of light and scatters shorter blue wavelengths, especially when the water is clear. But the early ocean is probably not clear in the same way. It contains large amounts of dissolved iron released from volcanic rocks and preserved in solution because free oxygen is almost absent. In a world without oxygen, iron does not rust and fall easily out of the water. It remains dissolved, giving the sea a possible greenish, grayish, or dark mineral cast. The familiar blue of Earth may not yet belong to Earth. This iron-rich water is one of the most important differences between the early ocean and the modern ocean. Today, oxygen changes the fate of iron. When dissolved iron meets oxygen, it reacts and forms iron oxides. The chemical family of rust, these particles become solid and settle out. In the early Archean Ocean, before oxygen becomes abundant, the chemistry works differently. Iron can travel through seawater in reduced form. It can mix through large regions of the ocean. It can feed certain microbial metabolisms once life appears. It can wait, silently, for the long future moment when oxygen-producing microbes begin to transform the planet. The first oceans also hold large amounts of dissolved carbon dioxide. Rainwater passing through a carbon dioxide-rich atmosphere forms weak carbonic acid, and volcanic gases add more acidity through sulfur compounds and other reactive materials. These waters may be more acidic than modern seawater, especially near volcanic sources. The acidity helps break down young basalt and other rocks, releasing calcium, magnesium, silica, sodium, potassium, and trace metals. Every wave against bare volcanic shore becomes part of a chemical exchange. Every fracture in the seafloor becomes a passageway for water and heat. The temperature of these seas is not fixed in a simple way. Some regions may be very warm, heated by a young planet with a greater flow of internal heat. Near volcanic provinces and hydrothermal systems, water may approach extreme temperatures. Elsewhere, as the planet cools and the atmosphere changes, surface waters may become more moderate. The evidence from deep time is incomplete, and the exact temperatures of the earliest oceans remain debated. Yet it is clear that they exist in a world far more geologically active than the present. Heat rises from below. Steam and gas rise from volcanoes. Impacts still disturb the surface. The ocean is young, but it is already being stirred by forces from sky, crust, and mantle. There is almost no free oxygen in these early waters. This absence changes everything. It changes the chemistry of metals. It changes the kinds of energy available to early life. It changes what minerals can form. It also means that the first organisms, when they appear, cannot depend on oxygen the way animals do now. Modern animal life is built around oxygen because oxygen allows cells to release large amounts of energy from food. But the earliest microbial life must work with other chemical pathways. It lives in an anoxic world, where energy comes from reactions involving hydrogen, sulfur compounds, iron, carbon dioxide, methane, and other molecules. This is one of the deep insights of the first ocean. To modern eyes, oxygen feels like the sign of habitability. To early Earth, oxygen would be absent, and later, for many organisms, toxic. Life does not begin in the world humans prefer. It begins, or at least takes hold, in a world of chemistry that seems harsh from a surface perspective. The early ocean teaches that habitability is not comfort. It is the presence of usable energy, liquid water, chemical gradients, and enough stability for complex reactions to persist. The seafloor of this ocean may be one of the most active places on the planet. Oceanic crust forms from basalt, dark and iron-rich, created as molten rock cools. Because the young Earth is hotter, the crust may be thinner and more fractured in many regions. Seawater enters cracks and descends into hot rock. As it heats, it changes. It dissolves metals. It reacts with minerals. It becomes enriched in hydrogen, methane, hydrogen sulfide, and other compounds, depending on the rocks it passes through. Then it rises back toward the seafloor and escapes as hydrothermal fluid. Where this hot fluid meets colder seawater, minerals precipitate, forming chimneys, mounds, and porous structures. These places matter because they concentrate what the open ocean spreads thin. The early sea is vast, but dilute. A molecule in open water may drift without meeting the right partner for a reaction. A hydrothermal vent, by contrast, offers surfaces, compartments, heat, and chemical gradients. Tiny pores in mineral structures can act like natural chambers. Iron and nickel minerals can help catalyze reactions. Alkaline fluids mixing with more acidic seawater can create energy differences across thin barriers, somewhat like the gradients living cells later use across membranes. Such settings do not prove a single origin story, but they show how geology may have provided a scaffold for the first steps toward metabolism. The ocean surface and the deep sea floor are very different worlds. At the surface, ultraviolet radiation strikes through an atmosphere without a protective ozone layer. Lightning may flash through volcanic clouds. Impacts may disturb the water and atmosphere. Near the seafloor, darkness offers protection. The pressure is high, but stable. The chemistry is rich. Heat continues even when the surface changes. This contrast gives the early ocean a layered character from the beginning. The surface may be hostile in one way, the depths in another, yet both create possibilities. The shorelines also play a role. With no plants or animals, coastal zones are shaped by rock, water, tide, and chemistry. If the moon is closer, tidal ranges may be stronger in some regions, moving water repeatedly across mineral surfaces. Wetting and drying cycles in shallow pools can concentrate molecules. Waves break fresh rock into smaller grains, increasing surface area for reactions. Volcanic islands rise and erode. Basins fill and evaporate. Some origin of life models emphasize shallow settings for these reasons, while others emphasize deep vents. The early ocean may not offer one single cradle, but many chemical experiments occurring at once in different corners of the young world. Over time, the reaction between ocean and crust begins to shape the planet's long-term carbon cycle. Carbon dioxide dissolves in rain and seawater, reacts with silicate rocks, and eventually becomes locked into carbonate minerals. This process is slow, but it matters deeply. It is one of the ways Earth can regulate climate across geological time. The same general process still operates today, as weathering removes carbon dioxide from the atmosphere and stores carbon in rocks and ocean sediments. The first oceans, by attacking fresh volcanic crust with acidic water, help begin a planetary habit of chemical self-regulation. These ancient waters also begin the story of salt. The modern ocean is salty because weathering carries dissolved ions from rocks into rivers and seas, while water evaporates and leaves many ions behind. In the earliest ocean, salts accumulate as water reacts with crust and as hydrothermal circulation exchanges elements between seawater and rock. Sodium and chloride become important components, though the exact chemistry differs from today. Seawater is not born with its modern recipe. It evolves, slowly, through the continuous conversation between rain, rock, volcanic gas, seafloor, and time. The first ocean is therefore not a peaceful blue beginning. It is hot in places, acidic in places, metal-rich, oxygen-starved, and chemically alive. Yet it is not merely hostile. It holds the essential ingredients of later Earth. It stores heat. It dissolves gases. It receives minerals. It softens climate. It creates gradients. It protects the depths from radiation. It links atmosphere to crust and crust to interior. Long before animals swim, long before algae color the water, the ocean is already performing the work of a living planet's foundation. In the present day, the memory of those first seas remains in indirect traces. It is found in ancient rocks that preserve chemical signs of iron-rich waters. It is found in hydrothermal systems that still bring mineral energy into the ocean. It is found in the deep relationship between seawater, climate, and the carbon cycle. The modern ocean, with its blue surface and breathing ecosystems, descends from a stranger ancestor. That ancestor is not gentle, not clear, and not familiar. It is a mineral ocean beneath a toxic sky, a vast, dark chemistry where Earth begins to become more than a cooling stone. Beneath the young ocean, far from the broken light of a toxic sky, the seafloor opens in cracks. Cold seawater slips downward through fractures in dark volcanic rock, moving through narrow passages where the crust is still warm from the planet's inner heat. The water descends into darkness, but it does not remain unchanged. It is heated, compressed, and chemically transformed. Minerals dissolve into it. Gases enter it. Its ordinary clarity becomes charged with iron, sulfur, hydrogen, methane, and other compounds drawn from the deep rock below. Then the water rises again. It returns to the seafloor not as the same seawater that entered the cracks, but as a hot, mineral-rich fluid, carrying the chemical memory of the crust. When it meets the colder ocean above, minerals fall out of solution and build fragile towers, chimneys, and porous walls. Some vents release dark clouds of metal sulfides, making black plumes that drift upward like smoke in water. Others release clearer, alkaline fluids through pale mineral structures. In this early ocean, such places may form again and again wherever heat, water, and fractured rock come together. These hydrothermal systems are among the most important settings in the story of early life. They do not depend on sunlight. They do not require a gentle shore, a calm pond, or a blue sky. They belong to a deeper logic. The young Earth is a planet filled with chemical gradients, and the vents concentrate those gradients into small, persistent spaces. Hot fluid meets cold seawater. Alkaline chemistry meets more acidic water. Reduced compounds from the crust meet dissolved carbon from the ocean. Across tiny distances, energy becomes available. Modern life is built around gradients. Every living cell maintains differences between inside and outside. Across its membrane, ions are unevenly distributed. This imbalance is not a flaw. It is one of the basic ways life stores and uses energy. In many cells, protons move across membranes through molecular machinery, helping produce the energy-carrying molecules that power metabolism. The deep insight of hydrothermal vents is that they may have offered natural versions of these gradients before true cells fully existed. Mineral pores could have acted as tiny compartments. Thin mineral walls could have separated fluids of different chemistry. Energy differences could have existed across surfaces before biology learned to control them. This does not mean that the origin of life is fully solved. The first steps from chemistry to biology remain one of science's deepest open questions. No rock from the Hadean preserves a clear record of the exact place where life begins. There is no fossil of the first cell, no preserved moment when non-living chemistry crosses into metabolism and heredity. Yet hydrothermal vents remain compelling because they provide several needs at once. They offer energy. They offer chemical building blocks. They offer mineral catalysts. They offer protected microenvironments. They offer continuity, because the Earth's internal heat can sustain them even when the surface is disturbed. In the early ocean, the surface world is unstable. Ultraviolet radiation falls without an ozone shield. Impacts still occur. Volcanic gases alter the air and water. Shallow pools may dry, boil, or be disrupted. But the deep seafloor has a different kind of stability. It is dark, cold, away from the vents, and pressurized, but its heat sources can persist. The same geological motion that makes the young planet restless also creates sheltered chemical oases. These are not gardens. They are not peaceful in the human sense. They are dynamic, mineral, and harsh. But they are steady enough for chemistry to repeat itself, and repetition is essential for complexity. The earliest life, if it appears in such a place, is microbial and invisible to unaided eyes. It has no skeleton, no shell, no movement that would resemble an animal. It is chemistry wrapped in a boundary, able to maintain itself and reproduce. Its world is not one of sight, sound, or color. It is a world of electrons, molecules, surfaces, and gradients. Energy is not gathered from sunlight, but from reactions between compounds. Hydrogen may serve as a source of electrons. Carbon dioxide may be transformed into organic molecules. Sulfur and iron chemistry may take part in early metabolic pathways. The first living systems are not separate from geology. They are extensions of it, shaped by the same reactions that move through rock and water. Modern hydrothermal vents help make this ancient possibility easier to imagine. In the late 20th century, scientists exploring the deep ocean discovered thriving communities around vents far below sunlight. These ecosystems are powered by chemosynthesis, not photosynthesis. Microbes use chemical energy from vent fluids to build organic matter. Around them gather animals that depend on microbial production, either by grazing, filtering, or hosting bacteria inside their own bodies. Tube worms, clams, mussels, crabs, shrimp, and other forms of life can flourish in the darkness because microbes turn geologic energy into biological food. The early Earth would not have had these animals. They belong to a much later chapter, after oxygen rises and complex multicellular life evolves. But the microbial foundation is the key. Chemosynthetic microbes show that sunlight is not the only pathway into a living ecosystem. Life can be built from the planet's own internal chemistry. This makes hydrothermal vents more than unusual habitats. They become windows into an older kind of biosphere, one that may resemble the first stable living systems on Earth. The mineral structures of vents also matter. A chimney is not just a pipe. It is a complex architecture filled with pores, channels, surfaces, and chemical boundaries. Within tiny spaces, molecules can become concentrated rather than lost in the vast ocean. Iron-sulfur minerals can help drive reactions that resemble parts of ancient metabolism. Nickel and other metals can interact with carbon compounds. Alkaline vent systems are especially interesting because their chemistry may create proton gradients similar in broad principle to those used by cells. In such environments, the line between geology and early metabolism becomes subtle. Rock does not live, but it can create conditions that living chemistry may learn to inhabit. There is another quiet insight hidden in this possibility. Life may not begin as a sudden spark, but as a long negotiation between water and rock. The earliest biology may emerge gradually from networks of reactions that become more organized over time. Some reactions repeat because the environment sustains them. Some molecules help make more molecules like themselves. Some boundaries become more effective at separating internal chemistry from the outside world. Eventually, a system appears that can maintain its identity, use energy, and pass information forward. At that point, Earth is no longer only geological, it has become biological. The deep ocean protects these early experiments from some surface dangers, but it also imposes its own conditions. Pressure increases with depth. Temperature changes sharply between vent fluids and surrounding water. Minerals can build and collapse. Fluids shift. Chemical supplies fluctuate. Early life must be flexible, simple, and deeply tied to its surroundings. It likely does not conquer the planet quickly. It persists in pockets, mats, films, and microscopic communities near energy sources. Its success is quiet. It does not announce itself through forests or reefs. It changes the planet molecule by molecule. Over time, microbial life spreads beyond its first refuges. It occupies sediments, shallow waters, rock surfaces, and perhaps many chemical niches across the ocean. Microbes become the first great engineers of Earth. They alter carbon cycling. They influence sulfur chemistry. They interact with iron. Later, some lineages evolve photosynthesis, and much later still, oxygen-producing photosynthesis begins to transform the ocean and atmosphere. But before that brighter revolution, there is the older dark foundation, the possibility of life learning to use the energy of the Earth itself. The connection to the modern world is profound. The metabolism of living cells still carries traces of deep chemical ancestry. Many essential enzymes depend on metals such as iron, nickel, copper, and molybdenum. Energy in cells is still managed through gradients across membranes. Microbes still dominate the planet in number, diversity, and biochemical importance, even though large life forms are easier to see. Beneath modern seafloors, within sediments and crust, microbial communities continue to live slowly, drawing energy from chemical reactions in darkness. The deep biosphere is not a relic. It is a living reminder that the planet's first successful strategies may still endure below sight. In the early ocean, a vent field rises from the black volcanic floor. Hot fluids shimmer into cold seawater. Mineral walls grow grain by grain. Tiny compartments hold chemical differences. Around them, the first pathways toward life may begin to organize in silence. There is no dawn here, no green surface, no sound carried through air. There is only warm chemistry flowing into dark water, and the patient work of a planet discovering how matter can become alive. The first oceans leave almost no clear shoreline behind. They cover the young Earth for immense spans of time, receive the first rains, react with the first crust, and perhaps shelter the earliest living chemistry. Yet when the present world searches for them, it finds only fragments. The most ancient ocean is not preserved like a lake beneath ice or a fossil, sealed in amber. It is scattered through altered minerals, faint isotopic patterns, and rare pieces of crust that have survived the planet's long habit of remaking itself. This is one of the quiet paradoxes of Earth history. The earliest oceans may be among the most important environments the planet ever forms, but they are also among the hardest to see. Their water does not remain in one ancient basin. Their seafloor does not sit unchanged beneath later sediment. Their coastlines do not survive as simple outlines on a map. Time does not merely bury them, it transforms them. The reason lies in the nature of Earth itself. Unlike the Moon, whose surface can preserve craters for billions of years, Earth is active. Its crust bends, breaks, sinks, melts, and rises again. Plate tectonics makes the planet alive in a geological sense. Oceanic crust is born at spreading ridges, moves slowly across basins, cools, grows denser, gathers sediment, and eventually descends into subduction zones. Once it enters the mantle, much of its old surface record is lost. This process is essential for Earth's long-term climate stability and chemical cycling, but it is also an eraser. It returns ancient seafloor to the planet's interior, like a page fed back into the furnace. The modern ocean floor is young compared with the Earth. Most of it is less than 200 million years old, a thin moment beside a planet more than 4.5 billion years old. This means that the original floors of the Hadean and early Archean seas are gone. They have been subducted, metamorphosed, melted, or folded into younger rocks beyond recognition. The deepest beginning of the ocean must therefore be reconstructed not from a preserved seabed, but from rare survivors and indirect signs. Some of the oldest rocks on Earth are found in places such as western Greenland, northern Canada, and western Australia. These regions preserve ancient crustal fragments, though even they have often endured heat, pressure, deformation, and chemical alteration. They are not pristine pages. They are more like manuscripts that have been burned, soaked, folded, copied, and partly rewritten. Within them, scientists search for signals that may speak of early oceans, early crust, and perhaps early life. The rocks themselves reveal how difficult this search is. Metamorphism changes minerals. Heat and pressure rearrange crystal structures. Fluids passing through rock can add or remove elements. Original textures can blur. A structure that once formed in shallow water may be stretched, recrystallized, and made ambiguous. A chemical signature that once reflected biology may be altered by later geological processes. The deep past does not lie openly. It must be approached with caution. One of the most delicate clues comes from isotopes, atoms of the same element with different masses. Carbon isotopes, oxygen isotopes, sulfur isotopes, and iron isotopes can preserve hints of ancient processes. Certain patterns may suggest biological activity, ocean chemistry, or interactions between water and rock. Yet such clues rarely speak with simple certainty. Non-biological processes can sometimes produce similar patterns. Later, metamorphism can shift the signal. The oldest evidence must be tested again and again, because the difference between a trace of early life and a product of geology can be very small. This gives the first oceans a ghostly quality. They are known less by their bodies than by their effects. Ancient minerals called zircons, some more than 4 billion years old, provide one of the most remarkable windows into this lost world. Zircons are tiny, durable crystals that can survive repeated cycles of erosion and metamorphism. Some preserve oxygen isotope ratios, suggesting that liquid water may have interacted with crust very early in Earth history. These crystals do not show an ocean directly. They are too small for that. Yet they imply that cool enough surface conditions and water-rock interaction may have existed surprisingly early, perhaps not long after the planet's most violent beginnings. This is a unique insight into early Earth. The young planet may not remain a molten inferno for as long as older imagination once allowed. Even in the Hadean, amid impacts and volcanic activity, there may be intervals when crust cools, water condenses, and surface environments become chemically active. The first ocean may not be a single stable world from the beginning. It may appear, retreat, vaporize in places, return with rain, and settle gradually as bombardment lessens. Habitability may arrive in pulses before it becomes a lasting condition. The absence of a clear record also shapes the story of early life. If life begins during this poorly preserved interval, its earliest chapters are almost entirely hidden. Microbes do not leave bones. They do not leave shells. Their bodies are soft, tiny, and easily destroyed. In later rocks, microbial mats can form stromatolites and other layered structures. But in the oldest rocks, even such forms are debated. A dark filament may be fossilized life, or it may be a mineral shape. A carbon signature may be metabolic, or it may come from non-living chemistry. Scientific restraint becomes essential. The mystery remains not because nothing happened, but because the evidence has been thinned by time. The erasure of the first oceans is not only loss, it is also part of why Earth remains habitable. Subduction removes carbon-bearing sediments and altered oceanic crust from the surface system. Volcanism returns gases to the atmosphere. Weathering draws carbon dioxide down again. This long cycle helps regulate climate over geological time. The same recycling that destroys the earliest seafloor also helps prevent the planet from becoming permanently frozen or overheated. Earth forgets in order to continue. The modern world carries this contradiction quietly. Mountains rise from the collision of plates that once held vanished seas between them. Volcanoes release gases from materials carried down at subduction zones. Continents grow through repeated melting, accretion, and deformation. The ocean's lost floors become part of new crust, new arcs, new rocks, and new landscapes. A person standing on a mountain belt may be standing above the remains of an ocean that closed hundreds of millions of years ago. The ancient sea is gone, but its matter is not absent. It has changed form. In the case of the earliest oceans, the transformation is deeper and older. Their waters cycle through atmosphere, crust, mantle, and later seas. Their chemical work helps shape minerals. Their interaction with rock begins pathways that later become part of carbon regulation, nutrient supply, and ocean salinity. Even without preserved waves or shores, they influence every ocean that follows. The present sea is not a separate creation. It inherits chemistry, water, and planetary systems that begin in those first uncertain basins. The search for the first oceans, therefore, becomes a search through distortion. It follows tiny crystals, altered rocks, isotope ratios, ancient terrains, and careful comparisons with modern geological processes. It accepts that the earliest Earth cannot be reconstructed as a perfect picture. It can only be approached as a layered memory. Some parts are missing. Some have been overwritten. Some remain as faint marks that become meaningful only when read together. Across the young planet, rain continues to fall. Oceans continue to gather, and crust continues to change. Beneath the water, sediments form and are destroyed. Minerals grow and are altered. Microbial chemistry, if already present, leaves only the lightest possible touch. The Earth keeps moving. Its surface refuses to become a museum. In this motion, the first oceans vanish as places, but endure as causes. Their waves are gone, their basins erased, their floors return to heat, yet their influence remains folded into the living planet, hidden in stone, in cycles, and in the deep patience of geological time. The early ocean holds iron in its quiet depths. For a long time, this iron remains dissolved, carried through greenish water because there is almost no free oxygen to force it out. The sea is an anoxic world, ruled by chemical pathways older than animals, older than plants, older than the bright atmosphere of the present day. Microbes live in this world by using what the planet offers: hydrogen, sulfur, methane, carbon dioxide, and metals released from rock. Their lives are small, but the scale of their influence is slowly becoming planetary. Among these microbial lineages, one group begins to change the direction of Earth history. Cyanobacteria, or their close ancestors, develop oxygenic photosynthesis. Light from the sun is captured. Water is split. Carbon dioxide is used to build organic matter. Oxygen is released as a waste product. To the microbes performing it, oxygen is not a gift to future animals. It is merely the leftover breath of a new metabolism, flowing into water that has never had to contain much of it before. This innovation does not transform the world all at once. The first oxygen does not immediately fill the sky. It enters an ocean filled with chemical substances ready to consume it. Dissolved iron, reduced sulfur compounds, volcanic gases, and organic matter react with oxygen almost as soon as it appears. In the beginning, the planet behaves like a vast sponge. Much of the oxygen released by microbial photosynthesis is drawn into reactions, locked away, or neutralized before it can accumulate widely. The most visible result of this long reaction is iron. When oxygen meets dissolved iron in seawater, iron changes form. It oxidizes, becoming solid iron oxide particles. These particles drift downward and settle onto the seafloor. Layer after layer accumulates, often alternating with silica-rich sediments. Over time, these deposits become banded iron formations, some of the most striking rocks on Earth. Their red, gray, and black bands are not simply geological patterns. They are the mineral memory of a planet learning to live with oxygen. These formations matter far beyond the ancient ocean. Much of the iron used by modern civilization comes from these deposits. Steel in buildings, bridges, ships, railways, machines, and cities is tied to microbial activity that took place billions of years ago. The modern industrial world, in this quiet way, rests partly on the waste oxygen of ancient cyanobacteria and the rusting of prehistoric seas. The cyanobacterial revolution also changes the meaning of sunlight. Before oxygenic photosynthesis, some microbes use sunlight in forms of photosynthesis that do not release oxygen. Oxygenic photosynthesis is different because it uses water, a resource spread almost everywhere across the ocean. By learning to take electrons from water, cyanobacteria gain access to a nearly limitless supply of raw material. This makes their metabolism powerful and eventually world-changing. The ocean itself becomes the source from which oxygen is made. In shallow seas, cyanobacteria grow in mats across sediment and rock. These microbial carpets trap grains, bind surfaces, and build layered structures known as stromatolites. In quiet lagoons and tidal flats, thin films of life climb upward through sediment again and again, preserving a record of slow growth. Each layer is delicate in the moment, but persistent across time. A stromatolite is not built by one organism. It is a community structure, a collective architecture made by microbes, sediment, chemistry, and patience. The world around these mats is still unfamiliar. There are no grazing animals to tear them apart. No fish casting shadows. No shells scattered across the seafloor. The shallows are broad, quiet, and mineral-rich. Sunlight passes through water that may still carry iron and other dissolved substances. The mats breathe oxygen into their immediate surroundings during daylight, forming tiny oxygenated zones, while much of the wider ocean remains anoxic. At night, respiration consumes oxygen again. The earliest oxygenated habitats may appear first as small daily pulses, thin halos around microbial communities, rather than a fully oxygenated sea. This is an important insight. The Great Oxidation Event is often imagined as a sudden switch, as though the planet moves quickly from no oxygen to oxygen. In reality, the rise of oxygen is slow, uneven, and contested by chemistry. For a long time, oxygen exists locally before it becomes global. It appears in surface waters, in microbial mats, and in shallow environments, then disappears into reactions. The atmosphere changes only after major oxygen sinks begin to fill. The ocean must rust before the sky can truly change. As more iron is removed from seawater, the chemistry of the ocean shifts. The greenish, iron-rich world begins moving toward a different state. Oxygen can persist a little longer in surface waters. New metabolic possibilities open. For organisms that can tolerate or use oxygen, the molecule becomes an energy advantage. Oxygen allows much more efficient extraction of energy from organic matter than many anaerobic pathways. This advantage becomes essential much later for active multicellular organisms. But at first, oxygen is also dangerous. It is reactive. It can damage cells. Many anaerobic microbes are harmed by it. The oxygen revolution is therefore not only a creation story, it is also an ecological disruption. The rise of oxygen transforms the atmosphere after a long delay. Once the ocean and crustal sinks absorb enough of the produced oxygen, some begins to accumulate in the air. This transition, associated with the Great Oxidation Event more than 2 billion years ago, marks one of the most important turning points in Earth history. Methane declines as oxygen reacts with it, weakening a greenhouse gas that may have warmed the young planet under a fainter sunday. The oxygen produced by life changes biology, climate, atmospheric chemistry, and the future direction of the planet. Oxygen also makes possible the gradual formation of an ozone layer. High in the atmosphere, oxygen molecules can be transformed by ultraviolet light into ozone, shielding the surface from harmful radiation. It does not make land habitable, but it begins a long process that later allows life to move into brighter and eventually terrestrial environments. The breath of microbes in the sea begins to alter the sky above barren land. The deep ocean does not become modern. For long stretches of the Proterozoic eon, oxygen may remain limited mostly to surface waters, while deeper regions stay anoxic or even sulfidic. The planet enters a layered state. Above, a thin skin of oxygenated water receives sunlight. Below, vast, dark waters continue older chemical traditions. Life exists between these worlds, shaped by gradients of oxygen, nutrients, and light. This layered ocean may help explain why complex life takes so long to flourish. The tools are forming, but the environment is not yet fully ready. In the modern world, every breath carries the legacy of that slow revolution. The oxygen filling lungs, feeding fires, weathering rocks, and supporting complex bodies begins with microbes in ancient seas. The rust-red bands in old rocks, the blue of the present sky, the energy of animal life, and the steel bones of cities are connected to that first microbial exhalation. The cyanobacteria simply live, multiply, and photosynthesize beneath the young sunday. Through their quiet persistence, the entire planet begins to change. After the first great rise of oxygen, Earth does not immediately become a world of animals, forests, and blue open skies filled with familiar life. The transformation is slower, quieter, and more restrained. The planet enters the Proterozoic eon, a span of deep time beginning more than 2 billion years ago and extending toward the threshold of the Cambrian period. Within this immense interval lies one of the strangest pauses in the story of life. often called the boring billion. The name sounds simple, almost dismissive, but the world it describes is not empty. It is a planet waiting, building, and holding its breath. The oceans of this long Middle Age are calmer than the first acidic, iron-rich seas, yet they are still far from modern. The surface waters contain some oxygen, enough to change chemistry and support new forms of microbial life. But the deeper waters remain largely oxygen-poor for much of this time. In places, the deep sea may become euxenic, rich in hydrogen sulfide, a compound with the smell of rotten eggs and a chemistry hostile to many oxygen-dependent organisms. From above, the ocean may appear wide and blue in places. From within, it is layered, uneven, and chemically divided. This layered ocean is one of the keys to the boring billion. The surface receives sunlight, hosts cyanobacteria, and produces oxygen. Beneath it, the deeper sea often remains dark and anoxic, separated from the upper layers by weak circulation and chemical boundaries. Oxygen does not easily penetrate downward. Nutrients do not always return upward in generous supply. The ocean becomes a world of thin, habitable skins over vast, restricted depths. It supports life, but it does not yet offer the stable, oxygen-rich environment needed for large, active animals. The atmosphere also contains less oxygen than the modern atmosphere. Estimates vary, and the record is complex, but oxygen likely remains at only a fraction of present levels for long periods. This matters because oxygen is not merely a gas, it is a way for cells to unlock energy. Complex multicellular bodies are expensive to build and maintain. They require communication between cells, structural support, controlled development, and steady metabolism. Without abundant oxygen, the energy budget remains limited. Life can become clever, but it cannot yet become large in the way later animals do. Yet beneath this apparent stillness, profound innovation continues. The Proterozoic ocean is the age of the invisible foundation. Eukaryotic cells, cells with nuclei and internal compartments, become established and diversify. These cells are more complex than bacteria and archaea. They carry mitochondria, energy-producing organelles that likely descend from once-free bacteria living inside another cell. Some eukaryotes later acquire chloroplasts through similar symbiosis, allowing them to perform photosynthesis. In this quiet age, life is not standing still. It is reorganizing itself from the inside. This is a unique insight into the boring billion. Evolution does not always appear first as large bodies or dramatic fossils. Sometimes its most important work happens inside cells. The architecture of complex life is being assembled slowly. Internal membranes, cytoskeletons, nuclei, organelles, genetic regulation, and systems for cell communication. These are not visually spectacular in the fossil record, but they are essential. A large animal can only appear after cells learn how to cooperate, divide labor, send signals, and maintain identity within a shared body. The boring billion is therefore not a gap in the story. It is the workshop behind the visible stage. In shallow seas, microbial mats continue to dominate. Stromatolites grow across tidal flats, lagoons, and carbonate platforms. Their layered forms rise slowly from sediment, sometimes as domes, columns, or broad, wrinkled surfaces. They are built by microbial communities, trapping grains and precipitating minerals. In a modern shoreline, worms, snails, grazing fish, and burrowing animals disturb the sediment constantly. In the Proterozoic, such disturbance is absent or minimal. The seafloor can remain sealed under living microbial carpets for long periods. The ocean floor has a smooth, bound texture, more like a living skin than the churned sediment of later marine worlds. These stromatolite landscapes are quiet but not simple. Within the mats, different microbes occupy different layers. Cyanobacteria live where light reaches. Other microbes process sulfur, carbon, nitrogen, and iron below. Chemical gradients form over millimeters. During daylight, oxygen may rise in the mat. At night, it may vanish. The mat becomes a miniature world, with its own vertical zones, cycles, and exchanges. Across broad, shallow seas, countless such mats help shape sediment, chemistry, and local oxygen conditions. The continents also change during this time. They grow larger and more stable. Cratons, the ancient cores of continents, become long-lived platforms. Supercontinents assemble and break apart through the slow motion of plate tectonics. The arrangement of land affects weathering, nutrient flow, ocean circulation, and climate. If continents are positioned in ways that limit nutrient delivery to the oceans, biological productivity may remain restrained. Phosphorus, a key nutrient for life, can become a limiting factor. Trace metals needed by enzymes may also be trapped under certain ocean conditions, especially in sulfidic deep waters. Life has increasing potential, but its supply lines are narrow. The boring billion may therefore be a story of limits. Oxygen is limited, nutrients are limited, ecological pressure is limited. With few large predators, grazers, or burrowers, the seafloor remains stable. Stability can support endurance, but it may also slow dramatic innovation. Evolution often accelerates when environments shift, when organisms compete, or when new niches open. During this long interval, much of the ocean may remain in a balanced microbial state, successful enough to persist, but not yet disturbed enough to transform rapidly. This long quiet has a modern echo. Many of Earth's most important processes today still depend on microbes rather than visible animals. Microbes cycle nitrogen in soils and oceans. They regulate methane. They decompose organic matter. They influence clouds, sediments, and climate. The Proterozoic reminds the present world that a planet can be alive without being visually crowded. It can be shaped by organisms too small to see, working patiently through chemistry rather than motion. The apparent quiet also prepares for later change. Sexual reproduction becomes more widespread among eukaryotes, increasing genetic variation. Simple multicellular forms arise in different lineages. Algae diversify. Genetic toolkits for adhesion, signaling, and development begin to accumulate. None of this yet produces a world of active animals, but it builds the capacity for one. The ocean is gathering potential in slow layers, like sediment settling onto an ancient seafloor. The boring billion is therefore not truly boring. It is subdued, restrained, and deeply productive in hidden ways. It is an age of microbial rule, low oxygen, quiet seas, and cellular invention. Its drama is not the chase of predator and prey, but the patient assembly of the machinery that later makes complex life possible. In its shallow waters, stromatolites rise grain by grain. In its cells, organelles hum with borrowed ancestry. In its chemistry, oxygen remains precious and uneven. The planet waits not in emptiness, but in preparation. Storing the future in forms too small for the eye and too important to ignore. Across the shallow seas of the Proterozoic, the seafloor wears a living skin. It is not yet crossed by crabs, stirred by worms, or shadowed by schools of fish. It is not covered in coral gardens or broken shells. Instead, wide tidal flats and warm lagoons are coated with microbial mats, thin but persistent layers of life woven from cyanobacteria and many other microorganisms. These mats cling to sediment, bind grains together, and turn the seafloor into something firm, textured, and quietly alive. In places where water is shallow and sunlight reaches the bottom, the mats begin to build upward. Their surfaces are sticky. Fine grains of carbonate, mud, sand, and silt settle onto them. The microbes need light, so they grow through the new dusting of sediment and create a fresh living layer above it. Then more sediment arrives. Again, the microbes rise. The process repeats through seasons, tides, storms, and long spans of quiet. Layer by layer, the mat becomes stone. These structures are stromatolites, some of the oldest and most enduring monuments made by life on Earth. A stromatolite does not grow like a tree. It does not have roots, a trunk, or leaves. It grows as a community, by trapping, binding, and sometimes helping precipitate minerals. Its shape depends on water depth, wave energy, sediment supply, chemistry, and the behavior of the microbes themselves. Some become low domes, rounded like dark cushions beneath shallow water. Some rise as columns. Some spread as wrinkled mats over broad carbonate flats. Their forms are slow, patient, and architectural, built not by intention, but by repetition. The world around them is quiet in a way that no modern tropical coast is quiet. There is the motion of waves, the pull of tides, the soft drag of water over sediment, and the faint chemical labor of microbial life. But there are no grazing snails rasping the surface, no burrowing shrimp turning the mud, no fish biting algae from rock. The absence of animals gives microbial mats an advantage. They can spread without being constantly eaten, torn, or churned apart. During the Proterozoic, this allows stromatolites to reach remarkable abundance and variety across shallow marine environments. Their beauty lies partly in scale. A single microbial cell is almost invisible, yet countless cells acting together can build structures large enough to shape a coastline. A mat only millimeters thick can influence oxygen, sediment stability, and mineral formation. Over long time, these tiny organisms create layered rocks that survive as fossils for billions of years. Stromatolites reveal a principle that returns throughout Earth history. Small life can make large geology. The planet is not shaped only by volcanoes, glaciers, and tectonic plates. It is also shaped by films of microbes working at the surface of mud. Inside a microbial mat, the world is layered with great precision. The uppermost zone receives sunlight. Cyanobacteria live there, carrying out photosynthesis and releasing oxygen. Just below them, oxygen may decline quickly. Other microbes occupy these deeper layers using sulfur compounds, organic matter, iron, or other chemical pathways. The entire mat can contain steep gradients over only a few millimeters. At noon, the surface may be oxygen-rich. At night, respiration may remove much of that oxygen. The mat breathes with the day, creating tiny cycles within the larger cycle of the planet. This gives stromatolites a unique role in the oxygen story. They are not the only source of oxygen, but they are visible expressions of oxygen-producing microbial life. In shallow seas, fields of stromatolites help create local zones where oxygen becomes more common. That oxygen reacts with minerals, affects nearby water chemistry, and slowly contributes to the broader planetary transformation. The oxygenation of Earth is not simply an atmospheric event. It is also a seafloor event, written in mats, sediments, and mineral surfaces. The Proterozoic seafloor, with its broad microbial carpets, also differs from modern marine sediment in a fundamental way. Today, many seafloor environments are mixed by animals. Worms, clams, crustaceans, and other burrowers move through mud and sand, disturbing layers and allowing oxygenated water to penetrate downward. This process is called bioturbation. In the age of stromatolites, before widespread burrowing animals, sediments can remain laminated and stable. Fine layers settle and stay intact. This helps preserve the delicate banding seen in many ancient rocks. The calm record of stromatolites is partly possible because the seafloor has not yet been biologically plowed. That absence gives the ancient ocean a texture almost impossible to recreate fully today. Many modern microbial mats survive only in restricted environments, places where grazers are excluded by high salinity, heat, dryness, or other stress. Shark Bay in Western Australia is a famous example, where living stromatolites persist in shallow, hypersaline waters. These modern examples are not perfect copies of the Proterozoic world, but they offer a glimpse. They show how microbial communities can still build stone-like structures when conditions protect them from the pressures of animal life. The decline of stromatolite dominance later in Earth history is therefore deeply meaningful. As animals evolve, graze, burrow, and disturb the seafloor, microbial mats lose their ancient control over shallow marine spaces. The rise of animal life does not merely add new creatures to the ocean. It changes the physical structure of the seafloor. It turns stable laminated surfaces into mixed sediment. It opens new ecological relationships, It transforms the quiet microbial world into a more restless animal world. In this sense, stromatolites mark the before time of marine ecosystems. The long age before the seafloor becomes animated by bodies that crawl, dig, bite, and hunt. Yet stromatolites are not primitive in the sense of being simple failures. They are successful, ancient, and efficient. They endure because microbial life is adaptable. Cyanobacteria continue to live today in oceans, lakes, soils, deserts, and symbiotic relationships. Their ancestors helped oxygenate the planet. Their communities helped build fossil records. Their metabolic strategies remain part of global carbon and nitrogen cycles. The living world still depends on microbial abilities first refined in deep time. The connection to the present is quiet but direct. The oxygen in the atmosphere, the carbon stored in carbonate rocks, the stability of sediments, and the cycling of nutrients all carry microbial signatures. Even modern reef systems, though built by animals and algae, rely on microbial processes that recycle nutrients and shape chemistry. The world of stromatolites has not vanished completely. It has been covered, complicated, and partly hidden by later life. In a Proterozoic lagoon, the water is warm and shallow. Sunlight reaches the bottom in pale green sheets. A broad mat darkens the sediment beneath the surface. Small bubbles of oxygen gather during the day and tremble between grains. The mat feels still, yet it is active in every layer. At the top, light becomes food. Below, other microbes receive the remains and transform them again. Sediment settles softly. The living surface rises through it. A dome begins. Not by haste, but by persistence. Across millions of years, these domes become fields. Across hundreds of millions of years, their fields become rock. They are cities without streets, reefs without animals, monuments without builders large enough to see. They stand as proof that the ancient ocean is not empty because it lacks movement familiar to modern eyes. It is full of slow construction. In the reign of stromatolites, life learns to build the seafloor one thin layer at a time. Rodinia gathers slowly, not in a single moment, but through collisions too vast and quiet for ordinary time to measure. Ancient continental blocks drift across the Proterozoic Earth, carried by plates that move only a few centimeters each year. Over millions of years, that small motion becomes a planetary rearrangement. Island arcs collide with cratons, ocean basins close. Mountain belts rise where pieces of crust press together. The scattered fragments of land begin to join into one of the great supercontinents of deep time. This supercontinent is called Rodinia. Its exact shape remains uncertain because the rocks that record it are old, altered, and spread across modern continents that have since separated again. Yet the general picture is clear enough. Around 1 billion years ago, much of Earth's continental crust is assembled into a vast landmass. Ancient North America, known as Laurentia, likely forms a central piece. Around it lie pieces that will much later become parts of Australia, Antarctica, South America, Africa, Siberia, and other regions. The map is unfamiliar, as if the modern world has been folded into a different design. Rodinia is not a green supercontinent. No forests soften its interior. No animals cross its plains. Life on land is still extremely limited, probably microbial in many places, clinging as films and crusts where moisture and chemistry allow. The surface of the land is largely rock, dust, mineral plain, and weathered slope. Rain falls onto bare ground without roots to hold the sediment. Rivers, where they exist, carry grains and dissolved ions toward the sea. Wind moves across open landscapes with little biological resistance. The land is quiet, but it is not inactive. It is being ground, cracked, heated, lifted, and worn down. Around Rodinia lies a vast ocean often called Mirovia. The name suggests a global sea, and although reconstructions remain debated, the idea is powerful. A single enormous ocean surrounds a single enormous landmass. Its waters stretch across much of the planet, broader than any modern ocean basin. There are no familiar Atlantic or Indian Oceans. no Pacific in its present form. The geometry of Earth is different. Land is concentrated. Water encircles it in immense continuity. The existence of such a superocean changes the way the planet breathes. Ocean currents depend on the shapes of basins, the positions of continents, temperature gradients, winds, salinity, and the rotation of Earth. With most continents gathered together, the pathways of circulation differ from today. Along the margins of Rodinia, shallow seas may host microbial mats and stromatolite fields. Far from land, the open waters of Mirovia may be nutrient-poor because nutrients often enter the ocean through weathering and runoff from continents. A superocean can therefore be vast, yet not uniformly fertile. Size does not guarantee abundance. This is one of the deeper insights of Rodinia and Mirovia. Geography controls biology. The arrangement of continents determines how much phosphorus reaches the sea, how currents mix the deep ocean, how oxygen spreads, and where productive shallow environments can form. Life does not evolve on an abstract planet. It evolves on a map. When the map changes, possibilities change. Rodinia's assembly may create stability, but it may also restrict the exchange of nutrients and oxygen in ways that help maintain the long, quiet character of the Proterozoic oceans. The interior of Rodinia is likely dry in many regions. A supercontinent can produce extreme climates because large inland areas lie far from the moderating influence of the ocean. Moist air loses much of its water near the coast or along mountains, leaving inner regions arid. Without plants, the surface may heat and cool more sharply. Dust and sediment move freely. The silence of such a landscape is geological rather than empty. Cracks form in exposed rock. Ancient mountains shed debris. Salt lakes may gather in basins and vanish again. The land carries no animal tracks, but it records the slow pressure of climate. Along the coastlines, the story is different. There, waves from Mirovia meet the edges of Rodinia. Tidal flats expand and contract. Microbial mats spread over carbonate platforms. Stromatolites grow in clear, shallow water. These margins are among the most important living zones of the time because they combine light, nutrients, and stable surfaces. The open superocean may be immense, but the productive fringe is where much of the visible life of the age gathers. Beneath the surface, Mirovia is probably chemically layered. Oxygen produced by cyanobacteria enriches some shallow and surface waters, while deeper regions may remain anoxic. In some areas, hydrogen sulfide may accumulate. This layered structure matters because it limits the expansion of eukaryotic life. A thin, oxygenated surface ocean can support certain metabolisms, but a dark, oxygen-poor deep ocean restricts the available habitat for organisms that need oxygen. The superocean becomes a world with a livable skin and a more difficult interior. Rodinia also influences the carbon cycle. When continents collide and mountains rise, fresh rock is exposed to weathering. Rainwater reacts with silicate minerals, drawing carbon dioxide from the atmosphere over long timescales. At the same time, volcanic activity associated with tectonics returns carbon dioxide through degassing. The balance between weathering and volcanism affects global climate. Supercontinents can disturb this balance because their assembly and breakup change mountain building, coastlines, erosion, and volcanic activity. In the long view, Rodinia is not only a landmass, it is part of the planet's climate machinery. The future of Rodinia is already contained within its structure. Supercontinents do not last forever. Heat builds beneath thick continental crust. Stresses accumulate. Rifts open. The land begins to crack. Magma rises into fractures. Long valleys form where crust stretches and thins. New coastlines begin as lines of weakness. What once joined together starts to pull apart. This breakup will eventually reshape oceans, climate, and life. But even in its stable phase, Rodinia carries the seeds of division. The connection to the modern world lies in the scattered remains of this ancient assembly. Mountain belts and rock provinces on different continents can be matched like pieces of an old torn map. Geological structures in North America correspond to ancient events recorded in other lands. Paleomagnetic clues reveal past latitudes. Mineral ages mark collisions and rifting. The continents now seem separate and permanent, but their rocks remember former neighbors. A coastline today may once have faced an entirely different continent across a vanished sea, or been pressed directly against it in the heart of a supercontinent. Rodinia and Mirovia also offer a way to understand the ocean as a changing architecture rather than a fixed background. Modern oceans feel permanent because human history is short. The Atlantic seems ancient, yet it is young compared with Proterozoic time. The Pacific is vast, yet it too is only one expression of a recurring cycle. Oceans open when continents split. They close when plates converge. A superocean such as Mirovia is not simply water filling empty space. It is one stage in a cycle that continues through Pangea and into the present arrangement of Earth. Across the Proterozoic world, Rodinia rests beneath a pale sky, surrounded by the enormous continuity of Mirovia. The land is broad, dry, and mostly bare. The sea margins glow with microbial life in shallow water. Farther out, the superocean stretches into dim, quiet distances. Its surface may receive sunlight and wind, while its deeper layers hold older chemical conditions. The world is stable, but the stability is not stillness. Plates continue to move, rocks continue to weather, microbes continue to build and breathe. Carbon moves between air, water, and stone. In this ancient geography, Earth seems to pause, yet the pause is full of preparation. The supercontinent shapes climate. The superocean shapes chemistry. Microbial life shapes oxygen. Hidden inside cells, complexity continues its slow assembly. Rodinia and Mirovia stand as the great stage of the long Proterozoic middle, a world of vast land, vast water, and patient transformation, where the planet's map becomes one of the quiet forces guiding the future of life. Around 720 million years ago, the long balance of the Proterozoic world begins to weaken. Rodinia, once gathered into a vast supercontinent, starts to fracture. Rifts open through ancient crust. Magma rises into widening cracks. New coastlines form where land slowly pulls apart. The shape of Earth changes again, and with that changing shape, the climate system begins to shift in ways that lead the planet toward one of the coldest chapters in its history. The Cryogenian period does not arrive as an ordinary ice age. Ice ages are familiar in the long record of Earth, with glaciers advancing and retreating across high latitudes and mountains. The Cryogenian is different in scale. Evidence preserved in ancient rocks suggests that glaciers reach low latitudes, perhaps even near the equator. The planet may become almost entirely covered in ice, or at least frozen so extensively that open water becomes limited and fragile. This state is known as Snowball Earth, though some models allow a slushier version with patches of open water near the tropics. The cause is not a single, simple event. It is a convergence of geology, chemistry, sunlight, and feedback. As Rodinia breaks apart, new volcanic and tectonic landscapes are exposed to weathering. Rain falls on fresh rock and reacts with silicate minerals. This process removes carbon dioxide from the atmosphere over long spans of time. Carbon dioxide is a greenhouse gas, and when its concentration falls, the planet cools. If the continents are positioned in warm, low-latitude regions, weathering can be especially effective because warmth and rainfall accelerate chemical reactions. In this way, the breakup of a supercontinent can quietly draw warmth out of the sky. As the climate cools, ice begins to expand. Ice reflects sunlight far more strongly than ocean or dark land. More ice means more sunlight reflected back into space. More reflected sunlight means more cooling. More cooling allows more ice to form. This ice-albedo feedback can become self-reinforcing, pushing the planet toward a frozen state. The process is not violent in the rhythm of a human moment. It unfolds across geological time, but once a threshold is crossed, the consequences become immense. The blue planet turns pale. The ocean changes first at the surface. Sea ice forms in cold regions and spreads. The reflective lid grows thicker and wider. As temperatures fall, the ice reaches farther from the poles. The sunlight that once entered the upper ocean is blocked or weakened. Photosynthesis declines wherever ice becomes too thick. Shallow marine habitats that once supported microbial mats are covered, chilled, or disrupted. The living skin of the Proterozoic sea begins to shrink. Above the frozen ocean, the atmosphere is dry and cold. The hydrological cycle slows because cold air holds less water vapor. Snow falls and accumulates over continents. Glaciers thicken and move, scraping rock beneath them into fine powder. Without plants, soils, or forests, the land offers little softness. Ice grinds directly across exposed stone. The sound of this world, if carried through air, would be the low pressure of wind over ice, the deep creak of moving glaciers, and the slow fracture of frozen surfaces under their own weight. Yet the tone of the planet is mostly quiet, as if sound itself has thinned in the cold. Beneath the sea ice, the ocean does not necessarily freeze solid from top to bottom. Water has properties that protect deep liquid layers, and geothermal heat continues to rise from the interior. Salt lowers the freezing point. Pressure also affects the stability of water at depth. A dark ocean may persist below the frozen lid, sealed away from air and light. This hidden ocean becomes a world unlike the open Proterozoic sea. It is cut off from winds. It receives little sunlight. Its exchange with the atmosphere is greatly reduced. Its chemistry begins to drift toward isolation. The deep waters beneath Snowball Earth are likely oxygen-poor in many areas. Without strong contact with the atmosphere and without widespread photosynthesis at the surface, oxygen cannot easily be replenished. Microbial respiration and chemical reactions consume what remains. In dark, isolated regions, anoxic conditions spread. Sulfur-cycling microbes may produce hydrogen sulfide, creating euxinic waters in some basins. Iron may become more soluble again under reducing conditions. The ocean beneath the ice becomes not only dark and cold, but chemically strange. In some ways recalling older chapters of Earth history, this is one of the important insights of the cryogenian world. Snowball Earth is not simply a story of ice covering water. It is a story of planetary systems being paused, compressed, and rearranged. The ocean is sealed. Weathering patterns change. Biological productivity collapses in many places. Nutrients accumulate in hidden reservoirs. Carbon dioxide from volcanoes continues to enter the atmosphere. But ordinary weathering feedbacks are weakened because much of the land is buried under ice. The planet becomes a closed mechanism, waiting for imbalance to build. Life does not disappear. Though its habitats become greatly restricted, microbes are resilient, and eukaryotic life has already emerged before the cryogenian. Survival likely depends on refuges. Some may exist near hydrothermal vents, where heat and chemical energy continue to rise from the seafloor. There, in darkness, chemosynthetic microbes can persist without sunlight. Other refuges may form in thin ice regions, brine channels, volcanic hot springs, subglacial lakes, or small areas of open water. If the planet is not entirely sealed, life becomes scattered, reduced, and patient. It survives not by dominating the planet, but by finding cracks in the frozen order. Modern Antarctica gives a partial echo of such possibilities. Beneath thick ice sheets, subglacial lakes can remain liquid for long periods. Microbes can live in brines, sea ice, sediments, and dark water where energy is limited. These modern environments are not exact copies of cryogenian Earth, but they show that life can endure in cold, sealed, low-energy settings. The deep lesson is that habitability is not always broad and bright. Sometimes it persists as small pockets of liquid water, chemical energy, and slow metabolism beneath a world that appears still. The Snowball Earth episodes may last for millions of years. During that time, volcanoes continue to release carbon dioxide. Because much of the surface is frozen, weathering cannot remove carbon dioxide efficiently. The gas accumulates gradually in the atmosphere, building a greenhouse blanket above the ice. The frozen planet is therefore not permanent. Its own geological engine is preparing the conditions for release. The same interior heat that sustains vents and volcanoes also begins, slowly, to load the atmosphere with the warmth needed to break the ice. Across the cryogenian Earth, the visual world is simple and immense. Continents lie under thick white sheets. The ocean is capped by ice, its liquid darkness hidden below. The sun rises over a bright surface that reflects much of its warmth away. Wind moves powdery snow across plains where no trees stand. Beneath the ice, water presses quietly against the underside of a frozen ceiling. Sediments settle slowly in darkness. Microbes persist in small worlds of chemistry and shelter. This frozen chapter reshapes the future. By stressing ecosystems, isolating populations, altering ocean chemistry, and preparing a later surge of nutrients and oxygen, Snowball Earth becomes part of the path toward more complex life. It is not only an interruption in Earth history, it is a deep transformation, a long, cold passage in which the planet's systems are reset. The Proterozoic ocean, once broad and quiet beneath the sky, becomes a hidden sea under ice, waiting for the slow return of warmth. Beneath the cryogenian ice, life becomes quiet, scattered, and difficult to imagine from the surface. The frozen planet seems almost closed to the Sunday. Vast ice sheets rest over continents. Sea ice spreads across ocean basins. The bright skin of the planet reflects sunlight away, and the familiar engine of marine photosynthesis is greatly weakened wherever the ice grows thick. Yet life does not vanish. It retreats into places where liquid water, chemical energy, and shelter remain. The survival of life through Snowball Earth is one of the most important facts in the history of the biosphere. Before the freezing, Earth already carries microbial life, eukaryotic cells, and perhaps simple multicellular forms. After the freezing, life continues and eventually enters a period of major ecological change. This means that somewhere, through millions of years of cold, organisms endure. Their refuges may not be large, they may not be continuous, they may be isolated, dark, and chemically unusual. But they are enough to carry the living world across one of its deepest environmental tests. One of the most reliable sanctuaries lies at the seafloor, around hydrothermal vents. Even when the ocean surface is sealed by ice, the Earth's interior continues to release heat. Seawater circulates through fractured crust, warms, reacts with rock, and returns enriched with chemical compounds. Around vents, temperatures are higher than in the surrounding deep sea. Chemical energy is available in the form of hydrogen, methane, sulfur compounds, and reduced metals. Microbes that use chemosynthesis can live without sunlight, turning geologic chemistry into organic matter. These vent communities may act like small islands of warmth beneath a global roof of ice. They are not safe in a gentle sense. The fluids can be hot, acidic, or alkaline, and chemically intense. But for microbes adapted to these conditions, vents provide continuity. They do not depend on seasons, sunlight, or open water above. The same type of environment that may have supported early life in the Archean can again become a shelter during planetary freezing. This creates a deep symmetry in Earth history. The darkness that may have helped life begin can also help it survive. Another possible refuge lies within the ice itself. Modern sea ice is not completely solid in the way it appears from a distance. It contains tiny brine channels, pockets of salty liquid trapped between ice crystals. Microbes can live in these channels, where liquid water persists at temperatures below the normal freezing point because of high salt concentration. Light can penetrate thin ice, allowing some photosynthetic organisms to survive near the surface. During Snowball Earth, if regions of sea ice remain thin enough, microbial communities may live within or beneath them, capturing weak sunlight and maintaining small local ecosystems. The ice becomes a habitat, not merely a barrier. Its lower surface may collect nutrients and provide a place where microbes attach. Brine channels may concentrate dissolved substances, bringing molecules close together in ways open water does not. In a frozen world, the boundary between ice and ocean becomes important. It is a dim, narrow zone, but it may preserve the connection between sunlight and life in places where the ice is not too thick. A third refuge may exist near the equator. Even during severe global glaciation, the tropics receive the most direct sunlight. Some climate models suggest that Snowball Earth may not be a perfectly sealed white sphere, but a planet with areas of thinner ice, seasonal openings, or slushy water near low latitudes. This version is sometimes called a slush ball model. In such regions, patches of open water or translucent ice could allow photosynthesis to continue. These areas would be small compared with the normal ocean, but biologically significant. In these equatorial pockets, cyanobacteria and algae may continue to produce organic matter and oxygen locally. The light is weak, filtered, and limited, but not absent. The water below may be cold and stratified. Nutrients may accumulate in unusual ways. Life persists close to the edge of its requirements. These sunlit refuges are important because eukaryotic photosynthetic organisms likely need at least some access to light to maintain long-term populations. The survival of algae through the cryogenian may depend on such places. Volcanic regions offer another kind of shelter. Even under ice, volcanic heat can create meltwater, hot springs, and chemically rich pools. Where volcanoes rise above or through ice, they can form local warm zones. Ash and dark rock absorb more sunlight than ice, increasing melting around them. Meltwater can collect in basins or flow beneath glaciers. These environments may be unstable, but they provide liquid water and chemical energy. Microbes can inhabit hot springs, wet volcanic sediments, and mineral-rich streams. Modern volcanic ice environments show that life can occupy such settings. In places where geothermal heat meets snow and ice, microbes live in warm water, mineral crusts, and melt channels. During the cryogenian, similar environments may appear across rift zones and volcanic provinces associated with the breakup of Rodinia. The same tectonic forces contributing to climate change also create scattered warm refuges. Earth's instability becomes part of life's survival. Subglacial lakes are another possible refuge. Beneath thick ice sheets, pressure and geothermal heat can keep water liquid. Modern Antarctica contains lakes sealed under kilometers of ice, where water remains isolated from the surface for long periods. During Snowball Earth, similar lakes may exist beneath continental ice. They may receive minerals from crushed bedrock and energy from chemical reactions. Sunlight does not reach them, so photosynthesis is absent, but microbial life can survive through slow metabolisms based on rock-water chemistry, organic matter, or compounds released from sediments. These lakes would be dark, cold, and still. Their ecosystems, if present, would be sparse. Yet sparseness does not mean failure. Life can slow down, cells can reduce activity, microbes can persist in low-energy states for long periods, waiting for better conditions or simply maintaining themselves through tiny chemical gains. Survival across deep time may depend less on abundance than on persistence. Coastal cracks, briny pools, and sediment pockets may also matter. As sea ice forms, salt is rejected from the ice crystals, creating dense brines that sink. These brines can collect in depressions, cracks, or beneath the ice. They may be harsh because of high salinity, but they remain liquid. Certain microbes tolerate extreme salinity today, and similar strategies may help ancient organisms endure. In sediments, organic matter buried before the freezing can provide energy for microbes. The seafloor mud becomes a slow pantry, feeding communities that metabolize at reduced rates in the dark. The survival of eukaryotes is especially important. Bacteria and archaea are extremely adaptable, but eukaryotic cells are more complex and often require more stable conditions. Their persistence through the cryogenian suggests that refuges must include places with enough energy, water, and chemical balance to support them. Some may live as resting stages, cysts, or slow-growing populations. Others may survive in sunlit ice margins or nutrient-rich meltwater environments. The lineages that endure carry forward the cellular complexity built during the Proterozoic. The modern connection is subtle but powerful. Life on Earth today is not descended from organisms that avoided crisis. It is descended from organisms that passed through crisis. The resilience of microbes, algae, and early eukaryotes during Snowball Earth helps explain why the biosphere is so difficult to erase. Life is not fragile in the way individual creatures are fragile. It is distributed, diverse, and chemically inventive. It can retreat into darkness, salt, heat, cold, sediment, ice, and stone. Under the cryogenian ice, the living world becomes almost invisible. No forests sway. No animals move across open plains. No coral reefs brighten shallow seas. Instead, there are microbial films near vents, cells in brine channels, algae beneath thin ice, organisms in volcanic meltwater, and slow communities in dark sediments. The planet appears still from above, but below the frozen surface, life continues in small, sheltered rooms. It waits inside the pressure of the ocean, inside the pores of ice, inside the warmth of rock, and inside the long patience of cells that need very little, yet preserve everything that will follow. The frozen world does not remain frozen forever. Beneath the silence of the cryogenian ice, Earth's interior continues its slow work. Volcanoes still breathe through cracks in the crust. Carbon dioxide rises into the atmosphere from vents, volcanic arcs, and rift systems. Under ordinary conditions, weathering would remove much of this gas. Rain would fall on exposed rock. Chemical reactions would draw carbon dioxide from the air, and rivers would carry dissolved minerals toward the sea. But during Snowball Earth, much of the land is sealed beneath ice. The great weathering machine is weakened. Carbon dioxide continues to accumulate. For millions of years, the atmosphere thickens with greenhouse gas above a planet that still reflects most sunlight away. The ice resists change because its brightness sends solar energy back into space, yet the accumulation continues. Slowly, the balance shifts. The greenhouse effect strengthens. Heat begins to stay. At first, the change is subtle. A slight softening at the margins, a thinning of ice in places where sunlight is strongest, a darkening where dust, volcanic ash, or exposed rock lowers the reflectivity. Then melting begins to feed upon itself. Dark water absorbs more sunlight than white ice. Exposed land warms more easily. More melting reveals more dark surfaces. The planet starts to move out of its long white sleep. The thaw is not gentle in a geological sense. It may unfold rapidly compared with the vast length of the freeze. Ice sheets that have grown for millions of years begin to collapse, retreat, and shed meltwater. Glaciers scrape backward across continents, leaving behind polished rock, scattered boulders, and thick deposits of ground stone. Rivers of meltwater run across bare land, carrying fine mineral flour toward the ocean. The water is gray, cold, and heavy with sediment. It braids across plains without forests, without grass, without roots. The world begins to sound again with flowing water. As the ice retreats, the ocean receives an enormous pulse of fresh water and minerals. Sea level rises as water locked in continental ice returns to the basins. The chemical isolation of the frozen ocean breaks apart. Surface water opens to the air. Winds begin to move across newly exposed seas. Waves return. The dark ocean beneath the ice, long cut off from the atmosphere, begins to mix with oxygenated surface waters and with the flood of nutrients arriving from the continents. The result is not a simple return to the old Proterozoic sea. It is a transformation. The sediments carried by melting ice are rich in the products of long glacial grinding. Over millions of years, ice has crushed bedrock into fine particles, exposing fresh mineral surfaces. When the thaw begins, these minerals weather quickly under warm, carbon dioxide-rich conditions. Phosphorus, iron, and trace metals enter rivers and seas. Phosphorus is especially important because it is a key nutrient for life. It helps build DNA, RNA, cell membranes. Without enough phosphorus, biological productivity remains limited. With a sudden supply of it, the surface ocean can bloom. This is one of the most important insights of the post-snowball world. The Ice Age does not simply suppress life and then end. It prepares a chemical feast by grinding continents, pausing normal circulation, and allowing nutrients to accumulate. The frozen interval loads the planet with materials that can later fuel biological expansion. The thaw opens the lid. Sunlight returns to the surface waters. Nutrients pour in. Organisms that survived in refuges find a changed ocean waiting around them. Cyanobacteria and algae respond to the new conditions. In sunlit waters, photosynthesis increases. Blooms spread where nutrients are abundant. The water may become green, cloudy, and rich with microscopic life. During the day, oxygen is released into the surface ocean. Some of it enters the atmosphere. Some sinks with organic matter. Some reacts with reduced compounds that have accumulated in deeper waters. The oxygen story remains complex, but the direction begins to shift. The planet moves toward a second major rise in oxygen, not as a single sudden event, but as a broad change in the balance between life, nutrients, burial, and atmosphere. Organic matter produced in these blooms falls into the deep ocean. Some is decomposed, consuming oxygen. Some is buried in sediments, removing carbon from the active surface cycle. Burial matters because when organic carbon is buried rather than fully decomposed, the oxygen produced during photosynthesis is not entirely consumed again. Over time, this allows oxygen to accumulate. Thus, the rise of oxygen depends not only on life producing it, but also on Earth burying enough reduced carbon to leave oxygen behind. The seafloor becomes part of the atmosphere's future. The post-glacial ocean is chemically unstable. Surface waters may become more oxygenated, while deeper waters still hold anoxic or sulfidic zones. Iron released from sediments and vents may react with new oxygen. Nutrient-rich waters may produce blooms that later decay and create local oxygen shortages. The ocean is not suddenly modern. It is a turbulent chemical transition, a world trying to find a new balance after millions of years under ice. Yet, instability creates opportunity. Gradients become sharper. Habitats diversify. Populations once isolated may spread, mix, and adapt. The rocks formed after the thaw preserve one of the strangest signatures of this transition: cap carbonates. These are layers of carbonate rock deposited directly above glacial sediments in many parts of the world. They mark a rapid shift from ice-covered conditions to warm, carbonate-precipitating seas. Their formation is tied to intense weathering under a carbon dioxide-rich atmosphere and to changes in ocean chemistry as the planet leaves the frozen state. They are like pale stone blankets laid over the debris of ice, a quiet geological punctuation at the end of Snowball Earth. In these cap carbonates and associated sediments, Earth leaves a record of extremes. Glacial deposits show ice reaching regions that were once near the tropics. Carbonate layers show the warm, chemically charged aftermath. Isotopic shifts record disturbances in the carbon cycle. Together, they reveal that the planet has passed through a state unlike almost anything in later history. The ocean is not merely a witness. It is the main chamber where the consequences gather. Nutrients, oxygen, carbon, metals, and surviving life all meet in the newly opened water. The connection to modern Earth lies in the relationship between climate crisis and biological possibility. The cryogenian freeze is destructive, but its aftermath helps create conditions that may support the later rise of large, complex organisms. The increase in oxygen, the expansion of algae, the restructuring of ocean chemistry, and the diversification of eukaryotic life all belong to the broader recovery. Earth's living world is shaped not only by stable comfort, but by transitions that reorganize the limits of life. As the ice disappears, the planet is not returning to what it was. It is becoming something else. The seas breathe more freely beneath the sky. Rivers carry minerals from newly exposed continents. Microbes bloom in the brightened shallows. The deep ocean slowly exchanges its dark, sealed chemistry with the surface. Oxygen begins to gain ground. The long quiet of the Proterozoic is disturbed, and the foundations of a more complex biosphere are strengthened. The thaw leaves behind a world washed clean in places, buried in sediment in others, and chemically renewed across the oceans. The white surface of Snowball Earth fades. Water darkens the planet again. Clouds form over open seas. Rain returns to exposed rock. In the ocean, the smallest lives multiply in the light, and through their quiet work, the future becomes more breathable. After the great thaw, Earth carries forward the memory of its lost oceans in forms that are easy to overlook. The ancient waters do not remain as the same basins, the same coastlines, or the same currents. Their floors are folded, buried, subducted, lifted into mountains, or dissolved into younger cycles. Yet their influence remains everywhere. It is held in stone, in the chemistry of the air, in the shape of continents, in the minerals beneath cities, and in the living systems that still depend on ancient oceanic inventions. The vanished seas of early Earth are not lost in the simple sense. They are transformed. The first iron-rich oceans leave behind banded iron formations. Those layered rocks formed when oxygen released by microbes reacts with dissolved iron in seawater. The bands are quiet, dense, and often beautifully striped, but their meaning reaches far beyond geology. They record the moment when microbial life begins to change the chemistry of the planet on a global scale. They also become one of the major sources of iron ore used by modern civilization. In bridges, railways, ships, tools, towers, and machines, there is a distant connection to ancient seawater turning to rust beneath a young sky. Carbonate rocks also carry the memory of old oceans. Limestones and dolostones form in marine settings where calcium, carbonate, and biological or chemical processes combine into sediment. Some are built with the help of microbes. Some are shaped by the shells and skeletons of later organisms. Some mark strange transitions, such as the cap carbonates laid down after Snowball Earth. These rocks may later rise into cliffs, mountains, plateaus, and building stone. A pale limestone wall on land can once have been seafloor. Its calm surface may hide the remains of microbes, shells, mineral grains, and seawater chemistry from a vanished world. This is one of the deep insights of Earth history. Oceans do not only occupy space, they manufacture memory. They leave chemical signatures, sediment layers, fossil traces, mineral deposits, and climate records. When an ocean disappears, it does not become nothing. It becomes archive. It becomes raw material for future landscapes. It becomes part of the continents that later seem dry and separate from the sea. Mountain belts often contain the remains of closed oceans. When continents move toward one another, the ocean between them narrows. Its crust descends into subduction zones. Its sediments are scraped, folded, and compressed. Its islands and seamounts may be accreted to continental edges. Eventually, when continents collide, the ocean is gone, and mountains rise where water once lay. This means that some high places on Earth are built from the ruins of ancient seas. Marine fossils can be found in rocks lifted far above modern sea level. The summit does not contradict the ocean. It preserves its afterlife. The same principle applies to the deep cycles beneath the surface. Oceanic plates absorb water and carbon-bearing minerals as they travel across the seafloor. At subduction zones, they carry these materials downward into the mantle. Some of that water and carbon later contribute to melting, volcanism, and the return of gases to the atmosphere. The ocean, therefore, participates in a cycle that reaches beyond its basin. It helps move elements between surface and interior. The vanished seafloor is not only destroyed, it is recycled into volcanic arcs, new crust, atmospheric gases, and long-term climate regulation. Modern climate stability depends in part on this ancient style of exchange. Carbon dioxide leaves the atmosphere through weathering and burial, then returns through volcanic activity over long timescales. Oceans mediate this process by storing carbon, transporting ions, and forming sediments. The early seas help establish the chemical habits that make Earth different from a lifeless rock. Their legacy is not only in old deposits, but in the ongoing ability of the planet to regulate itself across millions of years. The biological legacy is even more intimate. The oxygen in the atmosphere is not a simple feature of the planet's original condition. It is an achievement of life, built over time by photosynthetic organisms in ancient waters. The first cyanobacteria release oxygen into seas that cannot yet hold much of it. Iron and other reduced substances consume it. Only after long chemical preparation does oxygen rise in the air. Every animal breath, every fire, every high-energy metabolism depends on that long microbial transformation. The modern sky is partly an oceanic product. The structure of living cells also carries echoes of ancient seas. Many fundamental metabolisms evolve in water. Cellular chemistry depends on ions, membranes, gradients, and molecules that first become meaningful in aquatic environments. Mitochondria, the energy-producing organelles of eukaryotic cells, descend from bacteria that enter into symbiosis with other cells long before animals appear. Chloroplasts descend from photosynthetic bacteria. These events happen in the microbial world of ancient waters, and they shape the later evolution of plants, algae, fungi, and animals. The forest, the reef, and the human body all inherit cellular agreements made in deep time. The Proterozoic oceans, though long dominated by microbes, provide the foundation for complex life. Their low oxygen and nutrient limits slow visible evolution, but their hidden innovations are essential. Eukaryotic cells diversify. Sexual reproduction spreads. Multicellular experiments begin. Genetic systems for cooperation and development accumulate. By the time oxygen rises more substantially and environments become more favorable, life has already assembled much of the internal machinery needed for complexity. The quiet oceans are not empty waiting rooms. They are workshops. The Snowball Earth oceans add another layer to this legacy. Their ice-covered darkness restricts life, changes chemistry, and stores nutrients. The thaw releases those nutrients into surface seas, helping stimulate blooms and oxygenation. The later rise of larger, more complex organisms may be linked to this sequence of stress, survival, and renewal. The frozen oceans, therefore, become part of the path toward the animal world. Their severity does not erase the future. It helps prepare it. Even modern ocean life carries patterns shaped by ancient crises and opportunities. Microbes remain central to marine ecosystems. Phytoplankton still produce oxygen and draw carbon into the sea. Deep-sea communities still depend on falling organic matter and chemical energy. Hydrothermal vents still show that life can thrive without sunlight. The Hadean trenches still collect carbon, sediment, and organisms in the deep folds of the crust. The ocean remains layered, chemical, and connected to geology, just as it has been since the earliest chapters of the planet. The vanished oceans also shape human understanding. They reveal that Earth's surface is temporary. Maps are moments. Coastlines move. Seas open and close. Continents gather and separate. A dry plain may once have been a shallow marine shelf. A mountain may contain seafloor. A mineral deposit may be the breath of ancient microbes turned to stone. This perspective gives the modern world a deeper kind of strangeness. The familiar landscape becomes a slow oceanic memory. In the present, waves move over beaches, sunlight brightens the upper sea, and deep currents pass through black water far below. These waters seem immediate and complete, but they are part of a much older story. The ocean now covering the planet inherits chemistry from vanished seas, oxygen from microbial revolutions, carbon cycles from weathered rock, and life strategies first shaped in darkness and shallow light. Every tide belongs to the present, yet every tide also touches the past. The lost oceans of Earth are gone as places, but not as forces. They survive in rust-red rock, pale carbonate, folded mountains, volcanic gases, oxygen, cells, and the slow breathing of the climate system. They have no shores to stand beside now, no surface to watch under an ancient sky. Still, their work continues quietly. They are beneath the ground, within the air, inside living bodies, and deep in the memory of the planet, where water, stone, and life remain bound together across time. The forgotten oceans of prehistoric Earth no longer move beneath their ancient skies. Their waves have faded, their coastlines have vanished, their floors have been folded, buried, lifted, or drawn back into the warm interior of the planet. Yet nothing in Earth's long story disappears completely. The water changes places, the stone changes shape, the chemistry continues, the memory remains. In the modern sea, there are still traces of those older waters. Every tide belongs to the present, but it also belongs to a deeper rhythm that began when the first rains fell on a young volcanic world. Every breath of oxygen carries the distant work of microbes that once floated in ancient sunlit shallows. Every band of iron, every limestone cliff, every fossil shell raised far above the sea holds a quiet reminder that Earth has worn many faces before this one. The story of these lost oceans is not a story of endings alone. It is a story of transformation. Seas become mountains. Microbes become atmosphere. Ice becomes renewal. Darkness becomes shelter. Stone becomes memory. Across billions of years, the planet keeps changing, slowly and patiently, carrying forward what came before, in forms almost too quiet to notice. And now the present ocean moves on, under moonlight, under clouds, under the slow pull of tides. Its surface rises and falls, while far below, sediments settle grain by grain. The Earth continues its long breathing. Continents drift. Basins open. Old seafloor descends. Somewhere in the deep future, even the oceans known today will become part of another hidden chapter. For now, the waves remain, soft and steady, carrying the ancient story onward into darkness, into stillness, and into sleep.